Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous sessions, we have seen the instability of stiffened panels and failure stresses in the plates and stiffened panels. We have seen the various empirical relationships that are given by Stowell and Mayer and Gerard, how he proposed the formula and how he modified the formula and given the approach, and we have solved a problem also on that. And in the today's session we are going to discuss on tension field beams. So the learning outcomes in this module are: the students are able to analyze the stresses on the diagonal tension field beam, and the students are able to determine the direct loads in the flanges of a tension field beam, and if possible they are going to solve few problems that are stiffened panel to which the stiffeners are attached. So tension field beams. So, and we discussed the spars of the aircraft wings. Usually they comprise of an upper flange and a lower flange. Usually they connected by a thin web. So you can consider here. So this is a spar cross section what you are able to see here, and it consists of one upper flange and one lower flange, and usually it is connected by a thin web. So in this configuration, this is called as a spar, and if you look at the webs, so these webs are often such a thickness that they buckle under shear stresses at a fraction of their ultimate load. So the form of the buckle is shown in figure here, where the web of the beam buckles under the action of internal diagonal compressive stresses that is produced by shear, and which is leaving a wrinkled web capable of supporting diagonal tension only in a direction perpendicular to that of the buckle. So in this configuration, the beam is then said to be a complete tension field beam. So if you try to understand the diagram here, so this is the beam which we have here, and the load W is applied here. So because of this load, that W that is happened, you can see the diagonal tension in this direction that occurs, and the buckle will occur in a perpendicular to this direction of the diagonal tension, that is buckling. The direction of buckle is shown here, that is buckling will occur in this direction. Okay, so this is very important topic which we have, tension field beams, in which we can clearly see whenever the load that is applied on beam, so how the buckling will happen and in which direction buckling will happen. So all that we can see here through this diagram. So to understand more deep into this one, to predict the stresses that are associated with this buckling phenomena, so we consider one small element here, which ABCD, and in which you can consider the stresses also, sigma T you can consider, and then we are writing redrawing the diagram over here. So this is ABCD element we consider. So sigma T is nothing but the tensile stress you can consider, and then you consider any plane. So we considered one plane, that is FD plane, and again alpha is the angle of diagonal tension, and on this inclined plane we represented two stresses, that is sigma tau and sigma Z and tau. So sigma Z and tau, these are the stresses that are inclined, that are acting on the inclined plane. Now, so this is what the general. So we need to find the expressions for this in the coming slide. So now here, complete tension field beam. So we have seen the beam, and which is connected by two flanges, that is one upper flange and one lower flange, and which is again connected by a thin web. And these connected flanges areas, they are having a depth D between their centroids and the vertical stiffness, which are usually spaced uniformly along the length of the beam. It is assumed that the flanges resist internal bending moment at any section of the beam, while the web of thickness T, it resists the vertical shear force. So there is an assumption what we take is flanges usually resist bending moment at any section, and then the web, which is usually very small, and it resists the vertical shear force. So the effect of this assumption is to produce a uniform shear stress distribution through the depth of the web at any section. So if you consider at any section of the beam, let us assume that S is the shear force and tau is the shear stress that is given, and therefore we can write the shear stress as shear force by area. So where S is the shear force, and then area you can write it as T into D. And now consider the element what we had, that is ABCD of the web in a panel of the beam as shown in figure. And the element is usually subjected to tensile stress, that is sigma T, and produced by the diagonal tension on the planes AB and CD, and where alpha is the angle of diagonal tension. And if you look at the diagram on FD, we have already denoted two stresses. We considered FD plane as an inclined plane in that element what we considered, and we represented tau and sigma z, which are nothing but tau as the shear stress and direct stress is sigma z. Now if you try to consider the equilibrium of this diagram and FCD from the figure, and usually have, so this is sigma T what we had, and then we had A, B, C, D, and this is a plane what we considered FD, and we represented two stresses, that is direct stress sigma z and shear stress tau. Okay, and we have assumed even the diagonal tension, that is angle of alpha also we have considered here, that is alpha is taken here. So this is the angle alpha, which is the angle of diagonal tension. So from this you can consider the equilibrium of FCD. So FCD you can consider the equilibrium, and you can write sigma T into, that is equals to T divided by sin alpha cos alpha. By multiplying by 1 by 2 in the numerator and denominator, you can write that sigma T as 2 tau divided by sin 2 alpha. You can simply consider this equilibrium of the element FCD, and if you try to resolve the forces vertically, you can get this one. Okay, and next one, by substituting for tau and noting that in the case that shear force S as the load that is applied on the beam is nothing but W. So you can substitute S equals to W at all sections of the beam, and then you can get the sigma T as 2W divided by TD into sin 2 alpha, because tau shear stress we consider it as S by T into D, in which S can be replaced by W, and then you can write it as tau equals to W by TD and substitute here. So this is the formula that we got, which is nothing but what? Tensile stress corresponding to the diagonal tension, that is sigma T, that is equals to 2W by TD into sin 2 alpha. Next similar manner, and if you try to resolve horizontally on the element, and you are going to get that is sigma z into FD into T, that is equals to sigma T into CD into T into cos alpha, and in which you can write sigma z as sigma T into cos square alpha, because you can see here CD by FD also can be written as cos alpha. So cos alpha with another cos alpha, you are going to get cos square alpha. So sigma z equals to sigma T into cos square alpha, and we already know the value of sigma T from the previous slide, that is sigma T equals to 2W by TD into sin 2 alpha. So this you can substitute here, and you are going to get sigma z, that is equal to T by tan alpha. Again you can, tau by tan alpha, and tau also again you can substitute it as S by TD, and further W S can be substituted as W by TD, and you can substitute here, and you are going to get the sigma z, that is the direct stress on plane FD. Sigma z you can calculate it as W by TD into tan alpha. So these are the stresses, two stresses we calculated, that is one sigma T, that is a tensile stress corresponding to the diagonal tension, and the other one is nothing but the sigma z, that is nothing but the direct stress on plane FD. And the next one, we are in the similar manner, you have to calculate the direct loads in the flanges as well. So the direct load in the flanges, now let's consider the same diagram, and let's make a cross section here like this, or a plane, and let us try to represent them as plane M which is acting, and let's try to represent the forces. Let us consider FT as the force force in the top flange, and FB force in the bottom flange, and on this plane again we try to represent the stresses, sigma z as the direct stress and tau as the shear stress, and let us assume the length of the beam as z, and let us assume the depth as d, and again same that is W is the load that is acting on the beam. So this is the diagram which we considered for the determination of direct loads, or it is also called as flange loads, that is FT and FB. So FT and FB are produced by a combination of the bending moment, that is W into Z of the section, plus compressive action of sigma Z of the diagonal tension, because W into Z is going to give moment about this section, and another moment that is going to give is sigma Z, that is compressive action of sigma Z. Now if you try to take the moment about the bottom flange from this diagram, about this bottom flange, so what are the forces that give moment is, first one is Ft. So Ft and the perpendicular distance is this one, so that is Ft into D, that you are going to get moment about the bottom flange. So that is the first one we have, and then sigma Z. So sigma Z acting on this plane, first of all the stress, it should be multiplied with the plane on which it is acting. So you can consider this as sigma thickness T, and T into the depth is nothing but D. So sigma T into sigma Z into T into D is the area, into again the perpendicular distance from here to here is D by 2. So you can write it as sigma Z into T D square by 2. So Ft by D minus sigma Z into T into D square by 2. So this is the moment what we considered about bottom flange. Again we have W into Z also we have on the other one. So this will give the clockwise movements, and while these two gives Ft and sigma Z gives the anticlockwise movements, and correspondingly you can write along with the signs. Clockwise movement you can consider it as positive, and the anticlockwise movements you can write it as negative, and then you get sigma Wz equals to Ft into D minus sigma Z into Td square by 2. Then substituting for sigma Z from the previous session, that is sigma Z value we got, and when you substitute into this equation, you are going to get the formula for Ft, and that is equal to Wz by D plus W by 2 tan alpha. And now if you try to resolve the forces horizontally, you can get Fb minus Ft plus sigma Z into Td equal to 0. And we have seen in the previous diagram that Ft is there here, you can consider it as minus Ft, and Fb is there plus Fb, and sigma Z is also in the right direction, so you can consider it as sigma Z into T into D, that is equal to 0. So once you get Ft, and you can write Fb from this equation, and you can substitute for Ft, so that you are going to get the equation as Fb minus Ft plus sigma Z into Td equal to 0. Substituting for Ft from this in this equation, you are going to get the force in the bottom flange also, which is equal to Wz divided by D minus W by 2 tan alpha. Okay, so this is the force in the top flange, and this is the force in the bottom flange. So these are the two flange forces that exist in the beam what we consider. Okay, and again if you try to calculate the diagonal tension stress sigma T, if you consider another plane, earlier we considered the vertical plane. Now if you try to consider the horizontal plane, so this is the diagram what we have. Sigma T, again you can consider it as a tensile stress due to the diagonal tension, and now we consider the horizontal plane as Hc. Again we try to represent the stresses on this. Direct stress as sigma y, and the shear stress as tau, and alpha is the angle of diagonal tension. So for this also what we are going to do here, it is we are going to consider two equilibrium. One is the vertical equilibrium, other one is a horizontal equilibrium of the panel. So first we considered the vertical equilibrium of the element HDC, and when you do that, you are going to get sigma y into Hc into T, that is equals to sigma T into Cd into T into sin alpha, and from which you can write sigma y is equals to sigma T into sin alpha into, and you are going to get Cd by Hc, which again you can write it as sin alpha, so that one sin alpha with the other sin alpha it becomes sin square alpha. You are going to get sigma y, that is equal to sigma T into sin square alpha. So this is the vertical equilibrium of the element HDC. Similarly, if you calculate the horizontal equilibrium, and you can get vertical equilibrium we got here, and after that by substituting for T here we got T, and diagonal tension stress already we calculated in the previous one. So you can substitute here, and you can rewrite that equation, that is sigma y equals to S by Td into tan alpha, in which the S is replaced by W. So you are going to get sigma y, that is equals to W by TD into tan alpha. Okay, and the tensile stress sigma y on the horizontal planes in the web of the beam, it will usually cause compression in the vertical stiffeners, and each stiffener may be assumed to support half of each adjacent panel in the beam, so that the compressive load P in the stiffener is given by P equals to sigma y into T into B, and which becomes again sigma y you can substitute from here, that is W by TD into tan alpha into T into B you can substitute, and finally the compressive load in a stiffener, that is P, is given by WB by D into tan alpha. And again here you can consider the load P. If the load P is sufficiently high, the stiffeners will buckle, and the tests indicate that they buckle as columns of equivalent length, and that is given by LE equals to D divided by under root 4 minus 2 into B by D, for the condition where width is less than 1 point times the depth, and if the width is greater than 1 point times of the depth, simply LE equivalent length can be taken as D. And the maximum bending moment occurs at a stiffener, and is given by the maximum bending moment, that is M max equals to sigma y into T B square by 12. It is less like BD cube by 12 you can substitute for the cantilever beam, and so in which sigma y again you can substitute the value what we got, formula what we got from the previous slide, and then the maximum bending moment what we had got from here is WB square into tan alpha divided by 12 by D. So these formulas, the flange forces, the maximum bending moment, the load in the stiffener, so all these will, and the stresses, diagonal tension stress and the ultimate compressive stress, that is sigma Cy, compressive yield strength, all this formula will be used to solve the problems on complete diagonal tension field beam, followed by angle of diagonal tension. So the angle alpha adjusts itself such that the total strain energy of the beam is stored to be a minimum, and for the beams having all components made of same material, and the condition for the minimum strain energy leads to various equivalent expression for alpha, and it is given by tan square alpha equals to sigma T plus sigma F divided by sigma T plus sigma S, where sigma F and sigma S are the direct compressive stresses due to the diagonal tension in the flange and the stiffener. Okay, so by this tan square alpha, and you can able to get alpha, and here you can substitute the value for the sigma F as well as the sigma S. So sigma F, that is the stress in the flange, that is W by 2 AF into tan alpha, where AF is the area of the flange. Sigma S equals to WB by AS into D into tan alpha, where AS is the area of the stiffener. When you substitute sigma F and sigma C into this formula, you are going to get tan 4 alpha, that is equals to 1 plus TD by 2 into AF divided by 1 plus TB divided by AS. This angle of diagonal tension formula for alpha, which is very important, and usually the problems what we get from the tension field beams starts with this calculation of the angle of diagonal tension alpha. So you have to remember this formula, tan to the power of 4 alpha, that is equals to 1 plus TD by 2 AF divided by 1 plus TB by 2 AS, where AF is the area of the flange and AS is the area of the stringer. So that's it from this session. In the next session, we discuss about the incomplete diagonal tension field beam, and probably by a formula, and also the post buckling behavior of the plates. Thank you.